Kill -9.
Long story.
Hello and welcome to the Hackaday podcast. I'm Elliot Williams.
And I'm Al Williams.
This is episode 239, Overclocking, Oscilloscopes, and oh no, SMD out of stock. This week, leading off the news, we're happy to announce the finalists from the wildcard round of the Hackaday Prize. This was the fifth and final round. So 10 finalists from the 5 different rounds are all now in the running for the big prize, and they've got one more, well, by the time you're listening to this, only a few more days to get the final version of their project in before we freeze the websites and the judges have a look and award the big money prizes. But before we get to that, let's say congratulations to all the wildcard people, including this time a bunch of robotics projects. 2 of them were agricultural robots. And I think we're seeing kind of a wave of small scale agricultural robots, and everyone's kind of hacking on this idea. And I think it's kind of in the zeitgeist. So it's kind of cool to see them showing up in the wildcard round.
I think that's really awesome because, there's been a lot of commercial agricultural robots, but one of the things people don't realize, it's one thing to say, I'm going to make a robot that mops the floor at the local big box store, because the big box store has relatively level, relatively clean floors. It's well lit. It doesn't have, things don't just appear and disappear, rocks and holes and things like that. People, there are people, but it's just different, right? It's almost more of a challenge, I think, to say, I'm going to go out in this random field where there's varying weather conditions and varying soil. Sometimes it's muddy, sometimes it's dry, sometimes there's a big hump, there's a rodent that runs across. There's a lot of things to consider there. So it's one of those things that sounds easy until you get into it, and then it becomes actually pretty hard.
But because it's also so idiosyncratic, I think it is one of those things where, like, the hacker/DIY solution makes a lot of sense too, because, at least for the first while, you're going to need to be able to repair these machines and make sure they're doing the right thing and fine tune and all this, right? Certainly right now there isn't an off-the-shelf solution to do this for you. So it's actually really cool to see people taking, the design and the build decisions into their own hands, because that means then they're going to be able to fix it and improve it in the field. Literally. Another project that got featured here was the Open Book by Joey Castillo, and this is kind of Open Book version 3 or 4. I don't even know how long he's been working on this. We've seen him before, and first version of the Open Book was really neat. It was, kind of out of the blue, an e-ink book reader, and then this has been refined so many times now that it's, again, it's practically a new project, and it's really cool to see it taking this new kind of significantly more refined shape. And I think in the category most professional, which isn't really a category, would be Find My Cat, the open source pet tracker, which is just a supremely refined project. If you have a look at this, you'll think that it's a commercial product, but it's actually a hacker project, just done really, really right.
I've said that so many times, though. We live in a really interesting time because with all the fabrication technologies we have available to us now, it's so much easier to turn out something that's indistinguishable from, something that would have taken a product lab to do a couple of decades ago.
This is a journey into sound.
What's that sound?
What's that sound?
All right, well, that brings us to What's That Sound?
Well, that sure sounds like a acoustic modem handshaking. Now, I guess if I was a super nerd, I could tell you it was like V56 or whatever the actual standard was, but not that good. Or maybe it's a G2 fax, but it doesn't sound like it's got the beeping for the ranging for that. So I'm going to go with a acoustic modem.
That's a good guess. It's a good guess. I was trying to lead Tom into figuring this one out by mentioning that there's like a periodic repeating pattern in there. Mm-hmm. And there's also a dropout at the end is the real super clue to people who listened to the podcast 2 weeks ago. But it doesn't help you if you didn't. The reason I picked this is because I thought it was really cool. It is a recording from the read heads of an old floppy drive. Oh. And This was done to put it into an oscilloscope to try to figure out what the data was by actually like looking at the waveform in particular because it has this little dropout that's caused by a physical dent on the disc. What I thought was cool about this was, when I told Tom, it was magnetic data, he's like, "Oh yeah, totally. It sounds like one of those cassette tapes, old cassette tape data formats." I'm like, "Yeah, but it's kind of not that. But it is kind of that." And this is, I think, my revelation is that old floppy diskettes were really just cassette tapes, just round instead of long and thin.
But try listening to music on a floppy while you're jogging. So
Yeah, I guess that's right. Actually, I remember Jerry Ellsworth did a million years ago. She did a gimmick where she was actually recording audio onto floppy diskettes. She was running audio through the record heads and playing them back. It was a pretty cool hack. Yeah, so anyway, this is the sound of floppy data. And 9 people got it right, probably because I gave super good clues on that one. 3 people got it wrong in fun and interesting ways, including Chu Aaron Uck, Barbarian of North Campus, who said it was a radio in need of squelch oil. I didn't know there was squelch oil. Happy Swedish Hacker, it has to be some 80s home computer loading files from a tape recorder. So close.
so close.
And Apple G sounds like the intro to Cannonball by the Breeders, which is totally wrong. That goes like a... I don't know what he was thinking.
You got to play it backwards and speed it up.
Oh, maybe. Anyway, we've got 9 correct answers this week. Can you pick a random number from 1 to 9 inclusive?
Me?
Yeah.
Well, let's see how we're going to do that.
You could just, if you haven't looked at the spreadsheet, you could just make up a number.
No. It's number 2. Because I asked Google for a random number between 1 and 9, and it obliged me.
Oh, well, fantastic. Congratulations then to Frederick. Sound of captured data from a floppy disk, floppy_dent.wave, which is, of course, actually the exact file. So congratulations to Frederick and everyone else who listens to the podcast. I'll come up with something mind-boggling for next week. So stay tuned and listen for your chance to win a Hackaday podcast t-shirt. All right, you ready for some hacks?
Let's do it.
Overclocking Raspberry Pi 5's SoC to 3 gigahertz and 1 gigahertz GPU. The Raspberry Pi 5 came out last week, and I thought that was really interesting. I got an early sample, but I got it just on the day the press embargo was released for it, so I had to play around with it for like an hour and a half and then write something up super quick. I didn't even have time to take real photos. I ended up just using the Raspberry Pi people's stock photos for it. Now that I have some time, I've been kicking the tires on it, and it runs a lot hotter than the usual Raspberry Pis. And so that's why I'm interested in this article coming out of Tom's Hardware, where they're trying to see how fast they can run it. Because the old Raspberry Pis, especially the 4s and the second generation of the Raspberry Pi 4s, the ones that came out with the CM4, were way overclockable to the point that if you just like put a little bit of aluminum on there, you could run the thing at, 50% extra speed easily. And so I wanted to see if that was still the case with the 5s, and Raspberry Pi has custom designed a heatsink with a fan on it. So, an active cooler. And that's what the folks at Tom's Hardware use to figure out how fast they can push the thing. On the one hand, it's kind of unfortunate that you need a cooler for it, but on the other hand, then the cooler is so effective that they are able to run the thing, instead of the stock 2.4 gigahertz, they're able to run it at 3 gigahertz with some stability. So not bad. And this is, again, all on the stock, in quotes, Raspberry Pi active fan cooler. So not bad at all.
It's interesting, just as a meta thinking about overclocking, is it's become almost the norm, right? I've got a bunch of Raspberry Pi Picos that you can overclock, and they all seem to be able to overclock to pretty much anything you want within reason.
Oh, really?
My AMD processor on my computer overclocks with no problem. So it makes you wonder what the philosophy is there. Do you just say, well, it's kind of like saying this is normally $99.95, but for you today only it's $69.95. You go, oh, I'm getting a deal. Or, especially not so much Raspberry Pis, but maybe the things like the CPUs, you say, well, okay, you can overclock it. But of course, when it fails, we can go, oh, I don't know, it wasn't our fault. You overclocked it. So I don't know. I can't figure out what the angle is. Or, you got like the Rigel scopes where they obviously know you can hack the features into them and they don't care about you, but they do care that the big, the Fortune 100 companies aren't going to hack the features, right? They're going to pay the price. Yeah. So, but it brings a lot of market awareness. So is overclocking become the way to say, hey, look, we're cool. You can do something cool with us. You can get something out of us for free. I don't know.
I think it's much more engineer-y than that. I think they're worried about their, safety margin on the chips, right? And they just don't want them to be failing on you under normal conditions. So they're running them slower than, they absolutely could be. And in fact, this happens in the Tom's hardware test, is that one of them, I think Les Pounder is able to run his at 3 gigahertz forever, but then Avram does it and has it lock up a couple times. So, whether it's 3 gigahertz or 2.8 is really where you want to be, who knows? I think some of it's just process variation, right? They're hedging their bets enough that they can guarantee the thing will run comfortably at 2.4 gigahertz, so you don't have to worry about it. I'm actually interested myself, and we'll see. I'll probably have to give it a try and come out with an article next week. I'm actually interested in running these things slower and seeing how mellow you can go with them before you have to add a cooler at all. Because it's a big step from the Pi 4s up to the Pi 5s, where you before could get away with just passive cooling, maybe a heatsink if you're really feeling saucy. Whereas with the 5s, you probably want a fan on it. And I don't want a fan on it, for the power consumption and for the noise. I think it'd be a neat experiment to see how much you can kind of underclock and go mellow on the Raspberry Pi 5s and how much performance you can get out of them before you have to step up to a fan. And I think that's something we haven't seen and something that would be cool for people to know. Because in principle, the Pi 5s are a lot more efficient per megahertz than the Pi 4s are. It's just that because they can go twice as fast, they produce a lot more heat and need some cooling.
Well, and if you underclock, you'd think you might have some power advantage to that also, right? If you were trying to run off a battery.
You don't have to run
a little
fan.
bit longer.
You have the CPU running slower.
That was one of the claims to fame, the old RCA 1802 that Dan and I enjoy so much. It was totally static. So if you wanted to not consume very much power, you could just stop the clock. And then it consumed almost nothing until you started the clock again. You could literally single step that processor with a debounced push button, and just say clock cycle, clock cycle, clock cycle. So I would imagine underclocking it would appeal to a certain type of design, just like overclocking. I think overclocking just appeals for the same reason that we want to spruce up our cars and have big PCs. It's like, bigger's better, but sometimes less is more.
That's what I think. And actually, I saw a really great video last week from Sophie Wilson, who used to be a revolutionary designer at ARM, now I guess at Qualcomm, gave a talk at EuroPython on the future of microprocessors. And it's a really neat talk about microprocessor/CPU design and where we're at now. The thing that I had as a take-home lesson from that was that, we all know about Moore's law and packing more and more transistors into smaller spaces. And the other nice thing about these finer and finer resolutions of chip design is that they use less power per gigahertz, basically. And that's part of what we're seeing here in the Pi 5. It runs more efficiently than the Pi 4 because it's on a smaller die. But the decrease in power used is less than the density of transistors packed in. And so you get this chip that's kind of necessarily, just because of the way the physics is, but then also kind of paradoxically more efficient, but because the transistors are packed in even more tighter than that, there's more heat density and it needs to be dissipated. And this is kind of what happened to CPUs in general in 2003 is they kind of were going faster and faster and faster. And then from 2003, 2006 to today, basically clock speeds have been the same, but they've been putting more cores on. And the reason for that is simply because we got to this point where it was approaching the temperature of a nuclear reactor inside the chip, but you just couldn't go denser because even though denser meant more efficient, it was still packing them into so much less physical space that it was just a question of how you get the heat out.
Well, I probably won't live to see it, but in 30 years when hackers are wanting to decap what we consider new parts and they consider old parts, it's going to be unpleasant. In our day, you can take a ceramic chip and pop the lid off of it with an X-Acto knife, or if you're
chisel.
if you're skillful with a mill and some fuming nitric acid. I used to do all that, right? You can decap a regular part. But now all these larger chips are actually upside down for heat dissipation, right? So what you think is the top is actually the underneath part, and the face of the chip is facing down. So I don't know how they, I guess if I still had that job that I had, 20, 30 years ago, they must have some way that those people do that now where they can get in there and look at the front of the die and probe it and do all the things we used to do. But I have no idea how that would work anymore.
Yeah, I'll have to throw a link into a hack done by Bunny Huang where he actually discovered that on some of those upside down chips, you could see straight through to the die with infrared. And so he was doing an infrared microscopy setup and could see, but only with these chips that are built upside down, right? But he could see straight into the die on them without even decapping it, which I think is pretty cool. Anyway, I've thrown the link to that Sophie Wilson talk in there. You should absolutely see it if you're interested in microprocessor design. The side effect of this is she also explains why the Raspberry Pi 5 puts off more heat than the Raspberry Pi 4, even though it's a more efficient processor. So I thought it was a cool tangent, but it's also a talk you should go watch.
My first hack this week was from iForce 2D, and it's sort of a CNC machine. It's sort of a 3D printer. It's actually a soldering machine, and it's kind of interesting. It's very relaxing to watch. It's a pretty long video. It's about an hour. But, he's got what amounts to what you would think of as like a little CNC engraver base. But there's a thing that looks suspiciously like the filament feed on a 3D printer that's pushing solder through a Bowden tube. And there's as he jokes at the beginning, there's a hot end. It's literally a hot end. It's the soldering iron tip. And I guess the genesis of this is he makes or sells something where there's, I think, 114 pins, 112, I don't know, some large number of pins. And he got tired of soldering them by hand. So the machine actually goes, finds the pin, gets it hot, feeds a little solder, withdraws, and then moves on to the next pin. There's a lot of nuance to that. And I'm not sure. It seems like there should have been more to it than that, because I'm not clear that just saying, well, if I preheat the pin for 200 milliseconds, then I need this much solder to make a good joint. And in fact, several points through the video, there's a couple of times where there's like one or two joints that are not very good, or there's a bridge between pins that a human person would have said, wait, that I'm not going to finish off. Whereas this thing, of course, just keeps rolling. It finishes it, and then you just have to do a board inspection. Still neat, though. And it made me think of a couple of things. I mean, first of all, when you think of automating soldering, this is not what you think, right? So it was kind of out of the box. Instead of saying, well, I'm going to go and build a wave solderer or, the normal things that you see for doing soldering at scale. It was kind of I guess not an original idea. Certainly somebody's done this before, but I did think it was a little out of the box. And that got me to thinking. And I thought, well, I wonder if you could have a paste extruder extrude solder paste, and then literally the hot end would be melting the solder and applying it. It seems like that would be something fun to try. And again, probably like this, probably a lot of trial and error and nuance to get that to work, if it would even work at all. Jenny wrote this up, and I couldn't help but laugh. She had a XKCD linked at the end where it says, oh, I think I'll automate this task. And then, of course, the building of the automation becomes the entire task, and you lose track of the original task. So this kind of had that flavor. You could probably get wrapped around the axle. Even as not being the designer of this, I'm thinking, oh, you could put computer vision on it, and oh, you could do, million things. So I'm sure he's off on some wild tangent now, and we'll be making more improvements to the robot. It's pretty cool, though, because it shows how far the community's come on motion control, that none of this stuff really looks unfamiliar, right? The solder feed looks like a Bowden set up on a 3D printer. He used Linux CNC to do the motion control. This is another one of those things where 40 years ago, this would have been rocket science, and now it's innovative stuff, but it's not super amazing that all this stuff was able to come together and do this.
So you're not going to believe this, but I've actually seen the industrial machine that does this. It was
Really?
at Electronica, which is this trade fair they have in Germany every once in a while. And this was 6 years ago now. I can remember it still. I must have video of it kicking around. I'll have to see if I can find it. It was all in a box and everything, but it did do computer vision. It had a CV thing, and it looked almost exactly like this, except it was an even bigger scale. And I asked the rep there, I was like, why would you do this? And he said that there were tons of cases where, you've got parts on the board already that can't be subject to heat, and you just need to do a few last through-hole components, or they had some weird rework case where they would feed a whole bunch of boards through this thing to get touched back up and stuff. So I've actually seen these. I mean, I've seen the commercial version of these, the industrial version of these, and they look just like the hobby version. So I think that's really awesome. The other thing that Jenny mentions in the article here is that it's an interesting pathing problem. You have to get the soldering iron down there on the board, but then you have to kind of lift it up and watch out for the other pins as you're moving around. And it has to come down at an angle, and it has to meet like right in that joint. It's not as easy as it looks, but it's really a cool looking machine.
I would have said it's a hot project, but sure.
Oh, thank you. Thank you. Well, next up from me, the magic of a diode sampler to increase oscilloscope bandwidth. This is a video by Curious Mark about a diode sampler, which is, in this case, it's a big plugin that you can put ahead of a lower bandwidth oscilloscope to sample higher frequency signals. The trick here is that the high frequency signal has to be repeating, and we'll talk about that in just a minute. But in the video, he's demonstrating using a 100 megahertz scope, and he's got essentially a representation of a 4 gigahertz signal on it. What? This is a great demo of this diode sampler and how you can use essentially aliasing to bring down the signal from a higher frequency down to something you can see. And what's going on is that the diodes in question are making a really short pulse, and it's sampling the high frequency signal at these incredibly short windows and at kind of very high frequency, approaching the 4 gigahertz that they're on. I think of it as the old wagon wheel problem in movies, right? Where the film camera's shutter is running at 24 frames per second, and it's taking a very short picture 24 times a second. And when the wagon speeds up, its wheel kind of slows down, and then it eventually freezes, and then it goes back the other way, right? And when you get that frozen picture of it, it's not actually the same spoke in the same place every time. But because the spokes are all basically the same, you get this image that looks like the wagon wheel is frozen. And that's what's going on here. You're sampling this higher frequency waveform at a bunch of different points along its pattern, but each time doesn't come from the same cycle of the 4 gigahertz waveform. Each sample comes from, in fact, a different one, or maybe even separated by multiple periods. But when they are played out slow after each other on this 100 megahertz scope, it traces out kind of the average signal that the 4 gigahertz signal would have been. And that's basically what's going on here. What's really cool is that this is all done with like 1960s parts. And so if you look at the circuit diagram that's in the write-up here, everything is entirely doable today by the home builder. I mean, the transistors are boring. The diodes were fancy at the time, but they're actually just like kind of fast Schottky diodes now.
They're Schottkys, yeah.
Like, back in the 60s, you would pay a pretty penny for these, and now you could get them for 5 cents each. So it's a really, really cool technique. And a bunch of people wrote in the comments appreciating this. So apparently it's a technique that isn't widely known anymore. And hats off to Curious Mark for showing us all.
Yeah, I think it's natural hubris for all of us to think, well, we live in the technologically advanced society, and everything before was, bear skins and stone knives or whatever Spock says, right? So the problem is it's not true, and we've had a couple of pieces written about that. About, well, when you didn't have a CRT, how did you make an oscilloscope? And it turns out they did. Now granted they weren't gigahertz oscilloscopes with amazing sensitivity, but it's shocking how when you don't have any other option, you will figure out some way to get stuff done. And we see that consistently, right? I mean, if you told somebody we were going to go to the moon with the technology we had in 1969, actually much earlier than that, because you can't use new stuff, you'd have probably said, well, that's not feasible, but it was feasible. People did it, right? So think about this. I mean, you're old enough. When's the last time you saw a chopper or an alt mode on an oscilloscope, right? And it's kind of the same idea. In the 60s, if you had a multi-channel scope, you had to pick on whether or not the trace went back and forth between channels, or whether you did one channel, then the other channel, then the first channel again, and then the other channel. You don't see that anymore because we're beyond that.
Right.
That doesn't mean those things aren't still worthwhile to do. You would think in lower end stuff, even you could say, well, I could use one A to D and I could do a alt or a chop mode again, but people don't do that. They just throw more A to Ds at the problem. And a lot of the scopes I've seen recently will even have, it's kind of the reverse of this, right? My bandwidth is only 100 megahertz. So, or my sample rate rather. So I'm going to have 4 A to Ds so that I can sample a little bit slide in time and say I can do 400 megahertz of sampling, right? But I'm interleaving samples from 4 different A to Ds. It's not really a different idea, but it's a completely different implementation because we got different tools. But there was a lot of cool stuff going on, well, honestly, forever. If you look at some of the stuff we've written on really old stuff, ancient Greece, ancient Rome, and all that, they're doing some stuff you wouldn't believe, but it's just we don't have to do it that way, so we forget.
These old ideas are always worth knowing because you'll find a new application for it. And one of the great ones that comes up in the comments comes from Pigster6, who says he wants to measure something on a PCIe bus, but is just basically looking for an eye diagram. And eye diagrams are you take the rise time and fall time of a bit transition and you just plot a million of them over each other. And you can see if your rise times and fall times are fast enough because there's a hole in the middle. That's the eye in the eye diagram. And he's like, I wonder if you could do this same trick with eye diagrams, because when you do really high-speed digital stuff, you need a fairly expensive scope to diagnose this because it needs to be fast enough. Or does it? And I think that's a really neat idea here because, again, with the eye diagram, I think you're just averaging, a whole bunch of runs together. So my guess is this sort of bandpass sampling kind of whatever it is, diode sampler should work for that.
Without thinking about it too hard, I would think it would work if you had some gross problem. It might not work if you had one bad thing, right?
Yeah, you won't see the glitch. And that's the truth, is the thing you will miss with this, and the thing that just is drawing you one cycle for like every 200 cycles by taking little bits of each one, right? And so, yeah, if you've got a glitch in one of them, chances are you're going to miss it. And of course, that's like the selling point that the big scope manufacturers use for their like incredibly high sample rate scopes, is that, if you're into glitch finding, this trick won't work for you.
Well, I think that's really, I've said so many times, you don't have to know how an engine works to drive a car, but you can bet everybody at the Indy 500 driving knows exactly how the car works. And I think it's the same thing here. If you just say, well, I got a scope and this looks good. Well, yeah, but how is the scope really doing that? And so if I'm looking for that, 2 nanosecond glitch, it's hiding, right? I can't find it. And so I got to know that. So I think that's kind of an interesting idea that you could use it for in some of these more modern contexts for something like, I don't know, an eye diagram like you suggest or something else. There's all these high-speed tricks. And I mean, Jenny makes the point at the beginning, making an oscilloscope is relatively easy, while making a very fast oscilloscope is hard.
Yeah.
And so there's this whole other black art of high-speed design. And I actually pulled off my shelf right before we got together today. Analog Devices, oddly enough, has this wildly good collection of books that you can just go download off their website. And a lot of times they're books you could have got somewhere else earlier, and they basically got the rights to them and stamped their name on them. But one of them is some conference proceedings called High Speed Design Techniques. And it's got like 2 really good chapters on high speed A to D and applications of it. And it's really a different sort of animal. You just, the things you think make sense don't make sense at the high speed, and things that sometimes you don't think make sense. I mean, good example in the article, they use the RF tuned stub, right? And if you've ever seen that and not seen it before, it's just like black magic, right? Here's a piece of wire and it filters everything at 7 megahertz.
Right.
Why is that? Well, it's because it's a quarter wave and it's shorted at the end. And, if you go through it and if somebody will explain it to you, it makes sense. But man, just looking at it on a schematic with no explanation, if you don't know what that means, it just seems like, what? How's that possible?
Oh.
I really think that's one of those things that reading more about that it gives you a lot of insight into design that you don't necessarily have if you're just making LEDs blink and, working at audio frequencies.
And if you want to develop a little more intuition about how these diode samplers work, I actually wrote a piece 6 years ago now. Jeez.
2017. Yeah.
Say it with me, aliasing, but I go through kind of a nice, easy, approachable, hand wavy version of the DSP behind all this.
Next up for me, Jake Von Slot had another, I guess I'm on a CNC kick. This was the simple add-on makes cheap plasma cutters suitable for CNC use. And I have to confess, I'm not a dyed-in-the-wool welder, but it's one of those things I've always worked, or not always, but I frequently have worked places where we had people who were real experts on that and were, welding stainless steel to go at the bottom of the ocean and things that are not trivial. And it just amazes me how much science goes into what you think of as a pretty common operation. So apparently there's a lot of hacks out there to convert an HF torch into a pilot arc torch. And I'm not even sure I could articulate all the differences in that. The pilot arc part is you use a wire to electrically start a spark, but once the plasma ignites, you want the current to actually be flowing through the plasma. So the idea is, well, how do you, just get a little spark, and then once the current's flowing, you shut it off. And you think, oh, well, that's easy. Well, yeah, but it's at some, enormous amount of current. And I don't know if he ever actually says what it is, but I'm guessing it's hundreds of amperes or it's plenty. So the actual way he did this was took a core, split it, stuck a magnetic reed switch in the gap, glued it all back together with epoxy, and then that's his current sensor. And so, not rocket science, but it's just one of those things I thought was interesting. Will I build it? No, I probably need to get better at normal welding before I start trying to convert a HF torch into a pilot arc. But I don't know. There's just something about that just seems very powerful to have all this at your fingertips, right? I always say it's the mating call of the suburban homeowner. If you've ever been out in your front yard with a chainsaw cutting down a tree from a storm, if you start the chainsaw up, all your neighbors come out and want to see what you're doing, right, and talk about it. So I think it's kind of that way. If you say, "Ooh, I have a pilot arc plasma welder," I'm going to go, "Oh, I want to see that. I want to talk to you. I want to hang around while you're using it." I don't necessarily need one myself. I don't know. Are you a welder, Elliot?
I'm not. That's one of those things that I want to do. That's on my long list of skills I need to acquire. So no is the short answer. I'm sorely tempted by the rash of cheap welders out there, some of which are actually probably half workable.
It makes me super nervous. I saw one the other day on Amazon, like $39. And I'm thinking, well, this has to be like an electrical cord and some holders,
That's right.
It can't be much more than that. So,
Well, you can pony up for like the $70, $80 one. And I think that's actually getting to the range of reasonable. I mean, what's funny is that stuff all used to be, giant coils and really difficult MOSFETs. But those difficult MOSFETs have become easy now. And it's just, again, it's like the Schottky diodes in the diode sampler. It's just a bunch of IGBTs and they throw them in a box and there you go. Piece of cake. So yeah, maybe spend $60, maybe 90. Next up, power supplies without transformers is a write-up of 4 different designs by Swagatam. These are really interesting designs, but also kind of dangerous and to be savored with discretion. So go have a look at the transformerless power supplies, but be aware of the hidden danger. What is a transformerless power supply, you say? It is basically using a capacitor as the resistor in essentially a resistive divider. I guess it's a reactive divider because it's resisting AC, and capacitive reactance is a lot like resistance to an AC circuit. And so what's going on here is you pick a high voltage capacitor carefully to let just the right amount of current through, and then knock that down with something like a Zener diode to give you the DC voltage you want on the other side. What's dangerous about these is that the other side of the circuit, so one has this capacitor in it, the other side of the circuit is straight through. And so it's a wire going from your mains line straight to your little Arduino project or whatever. And if the neutral wire is really neutral and really doesn't carry voltage on it, this is in principle totally safe. If you plug that plug in the opposite way, then the live wire is the neutral and you are risking touching 120, 240 volts. So danger.
Let's play Trust Your Electrician, right? So.
Yeah, and I've seen these things in the wild, but they're always in cases where the end user will never, ever come in contact with it. And I think that's kind of the application for these transformerless power supplies. They make sense if it's inside a plastic case. For your 5 volt, 3.3 volt Arduino project where you're pressing a push button, it gets dangerous. So again, definitely take care.
So these were actually really common when I was younger. You saw a lot of hot chassis radios and TVs.
Yeah.
And, you're right. You normally wouldn't touch anything, although you might get a little tickle from a metal skirt on a knob or something, right? That was just part of life. But one of the first things I learned was you never touched, and I still do this to this day, you never touch a piece of metal like a chassis on a TV with your normal hand, because if it is powered up, electricity will make your muscles spasm and you'll death grip it. So we were always taught to touch it with the back of our hands, right? So then if your muscles contract, it just blows your hand away from the chassis, and you get a little shock, but you're not death gripped until somebody figures out they need to unplug it or throw the breaker. I don't know. It's one of those things where I'm sure saving the 82 cents is good, but it does seem like these days it's not that big a deal unless you're just making billions of things on a tiny, tiny margin. The old TV sets, and I'm sure many people remember this, you mentioned if there's no way the end user can touch it, well, they all had those cheater cords in the back of them, right? So when you took the back off, the cord came off with the back. So if the back was open, there was no way to power it. And so, of course, you had a cheater cord to be able to plug it in without the back on. And we always used to say, all you needed to fix anything was a heater, a cheater, and a beater, right? Meaning, and I have heard somebody lately say, I thought it was heater, cheater, and meter, and I thought, oh, that's actually better, but I don't think that's what we used to say. I think it was a hammer, the beater, right? So, soldering iron, a hammer, and a cheater cord. So you don't see cheater cords anymore, and you don't see TV degaussing coils anymore, and you don't, all this nostalgic stuff. For some reason, we're stuck on CNC and nostalgia. I don't know why.
Well, the good news is you don't see these circuits very much these days. Usually you do have a transformer and a switcher in there, because that's gotten a lot cheaper. Part of the reason I'm interested in this, and part of the reason it's good to talk about these circuits, and go back and check out an article I wrote about them, The Shocking Truth About Transformerless Power Supplies, back in, 6 years ago. That was fun. I found one of these in a switch that I was taking apart. It was a remote controlled radio switch for the power lines, and needed to diagnose it. And that's what led me down this rabbit hole initially. And I think that's where it's worth knowing about these circuits. Like, maybe you don't want to ever build one for yourself, but say you run into one in the wild, it's good to know, A, that you're looking at something that could be dangerous. So be very careful. And B, now you know how it works, you know how to diagnose it. And I think that's useful. In that article, I'm looking at it now, there's a picture of me hooking up a scope to this thing and verifying that it puts out 5 volts, which it really does. It's pretty cool for just a capacitor in line with line voltage, right? But what I did when I took this picture is I turned the device off, I clipped my scope leads to it, I walked away, and then I turned the thing back on. My hands were never near this thing when it was live. As a take home, I actually got that tip from Jenny, who wrote up a really awesome bit about working safely with line voltage, because she used to do TV repair, so she knows this stuff very well. And the tip is turn it off, power everything down. If you're going to make readings where you have to put probes on things, put the probes on with the power off, set your meter up, walk away, flip the power switch back on, read, turn it back off, and then you can pull your clips back off. You won't get hurt at all, and you can make these kind of otherwise sketchy readings inside of devices that might kill you without getting hurt.
Well, and you got to be careful too if you've got trying to make an isolated measurement, right? If your scope's grounded, they have all the special probes for that and all, but most people do not have them, right? So
right, this was a battery-powered meter, not an oscilloscope that's plugged into the wall. Because that's where you need whatever, those isolating transformers and so on. But anywho, if you're playing with one of these circuits in the wild, be careful, folks. And make sure you're using an X1 or X2 rated capacitor, because the capacitor is kind of a special capacitor. It has to be able to take this kind of 60 hertz pushing and pulling that you get with line voltage.
Well, I saved my favorite for last this week. Weekly Salamander 78 has built a CPU from discrete transistors. It's one of those things where you go, well, why is that interesting? But I think it's a rite of passage. I think at some point everybody's at least thought about building a CPU out of something, whether it's relays, tubes, transistors, FPGA, whatever. I think everybody who's got any involvement with this at least toys with that idea at some point. This one's pretty impressive. And what I thought was even more impressive, it had 2,000 individual transistors. That's cool. But he has this online interactive book, which I think is going to get added to. But it's pretty interesting. You go in and it says, well, how do you make a register? How do you build a processor from the ground up? How do you build the decoder? How do you make logic gates from FETs? And so, if you've ever been curious about that, it's a pretty good presentation on how that works, and I was pretty impressed with that. It's kind of an interesting choice. It's an 11-bit computer, and it reminded me back in the old days when everything was bit slice or even like this, just put together. You'd get like a government contract, and you would go, okay, well, the requirements say we have to have this, go to numbers up to this amount. So that's going to take a 14-bit CPU, and that's what you would build, because a 15-bit CPU would cost, extra, lots extra. So you used to see all these odd-sized machines from companies like Beckman and stuff that would just built for some very specific purpose and had a very specific word size for that. The other thing that I'm surprised we don't see more of, I think with 2,000 transistors in it, this actually has a pretty parallel architecture. But, a lot of the early machines that used tubes and even relays had more serial architectures, right? And that worked well with Mercury delay line memory. But it also worked well because my ALU just has to do 1 bit at a time. I don't have to go, here's 11 bits or 16 bits or 8 bits. I can just say, here's a bit, here's another bit, here's another bit. And that cuts down on the devices a lot. Here's the funny part, though, Elliot, and I've written about this. We're on the Wayback Machine again today. You had a 2017 article. I wrote this in 2015. Is, building the CPU, if you want to do anything practical, is almost the easy part to this. The hard part is coming up with all the tools and everything. So you've got two choices there. You can say, oh, I'm going to write a clone of a Z80 or create a clone of a Z80, and then I've got all these Z80 tools and I can boot CPM on it. Well, that's great, except that doesn't really give you much creativity or, it's a great exercise, but you want to do something for yourself probably, right? Well, okay, good luck, because now you need to write the assembler. And if you want a C compiler, you're going to have to at least port one over. And if you need an operating system, you better do that as well. And you think, well, that's ridiculous. Nobody does that. Untrue. In 2017, we had an article, FPGA computer covers A to Z. And that was what was so impressive about that, is that computer had, a graphics card and a language that wasn't any known language, I don't think, but it was, not assembly language. and he had games written for it. And so it was really odd to see something with that breadth of support that wasn't a clone of some other computer, right? It was just some completely unique computer. We've seen a couple of those. I just like to pick on that one, and I did like the name of it. It was the A to Z. I've gotten where I designed a lot of CPUs, some of them serious, some of them not so serious. And I got so tired of writing the assemblers for it, I need to put a link in for that. But I finally wrote a one universal cross assembler that actually uses the preprocessor in ways I'm ashamed to confess to. I mean, it's really the ugliest C preprocessor hack you've ever seen in your life. But it works, and I can make a pretty simple assembler for most of the stuff I build in about 15 minutes with that. And then it works like all the other ones, right? It has all the same output options and everything. So that is a serious problem is, okay, I've built my CPU. Now what do I do with it and how do I use tools for it? If you're not that invested to go find 2,000 transistors and figure out how to hook them up and then write all your own stuff, I also put a link to an article we did where there's a site where you can actually build a little fun CPU in your browser, and it kind of helps you and gives you little exercises, and you kind of drag and drop and make circuit blocks. It's kind of fun.
Yeah, I remember when we were doing Voya's badge last year, it was this, Voya made up this 4-bit CPU for it, and you had whipped up an assembler for it in like record time because you already had this infrastructure built out for it. I thought that was super cool.
That was in fact the universal assembler, and it's running on one of my servers, and I just stuck a web interface on it. So yeah, but it is the ugliest hack. I mean, you want to talk about Hackaday, this is the hack right here. I challenge you to go look at how it works, and you'll shake your head and wonder why I'm still left to roam in public. So,
all right, my first quick hack this week comes from Gord Payne. It is an entry in our Halloween Hackfest challenge. Treat Trough of Terror is actually pretty cute. This one has a big chute and a bunch of LEDs and an Arduino that powers it. Pumpkin opens its mouth, the candy slides out with glowing lights. The kids retrieve it at the end. Pretty sweet. The next Halloween hack I've got comes from Ronald McCallum. Halloween Hackfest Ouija board robot is even creepier than the real thing. This is a robotic hand and arm powered by a Raspberry Pi that moves around the Ouija pointer thing. It's lit underneath, it glows, and it spells out words for you. This is a pretty awesome project. I just love goofy mechatronics projects for Halloween. And both of these should remind you to enter the Halloween Hackfest. Head on over to Hackaday.io, check out the contests, go on and enter, get your project in before Halloween, and you will be one of 3 people who could possibly win a $150 DigiKey spending spree. This project's also co-sponsored by Arduino, and there's some Arduino swag in the box too. And my last quick hack, at last, faster OpenSCAD rendering is on the horizon. This is work done by Ochafik to port OpenSCAD over from the relatively slow CGAL library to the blisteringly fast Manifold 3D rendering library. And blisteringly fast is like a factor of 100 speed up at times. So if you've been one of those people like me who doesn't use the Minkowski operator to round off your edges because it just takes like half an hour to chunk through the thing, it will only take 20 seconds now. And if you have multiple processors, it's going to get cut down even faster because Manifold works with multiple cores, whereas CJL is single-threaded. This is going to be a huge breakthrough for OpenSCAD, and if you compile it yourself, you can get in on the action right now.
yay.
Yay!
Oh, my 3 quick hacks this week. Sayaka had the fixing a C64 with a cheap $20 oscilloscope. So, you see these $20, $10 oscilloscopes, $8 logic analyzers. You think, well, what are they good for? Well, it turns out if you got old computers, they're great because we didn't have that good of equipment back then anyway. So The little 5 megahertz scope is probably better than the guy that designed the computer had. We'll have to ask Bill Hurd what he had. So I think that was an interesting one. The other one was from a CNBC report, and it's kind of interesting. Google has an augmented reality microscope that might help diagnose cancer. So I'm not sure what their rationale is for being in that space, but good for them. I think it's a great thing. And it made me wonder, I wonder if there's other things that our community might be doing that could help any number of things with augmented reality or virtual reality. It seems like there's still a lot of floundering, and what is that really good for? What could it be used for? It'd be a good space for somebody to come in and do something really disruptive. And last but not least was from Andrew Menadu. He had a device with a mask-programmed ROM. The title's a 1970s mask ROM MCU spills its secrets. So a lot of these chips that are used in large production runs don't have EEPROM or flash memory, especially in those days. They didn't have any flash memory. They literally just have their program encoded on the metallization layer on the chip. So they just took off metal where they didn't want it and left it on where they wanted it. And even later than the 70s, they might have like an EEPROM, but there's no window to erase it. So that's not really mask programmed. But a lot of times there's these processors, the programs in them, you can't really get it out of them, and there's no way to get it to work. He got lucky on this because that particular chip had a test input for doing testing that allowed you to say, don't load your program. I'm going to load a program from you externally. And so he figured out how to do that, load a program into it that then read what was on the mask ROM and dumped it out. And so that was pretty clever. Probably one of those things that's not insanely generally applicable because it sure depended on them having that test mode in it. But I thought it was very clever, and I enjoyed seeing it. As all this old equipment gets even older and you can't get replacement parts and things, being able to dump the ROMs out of these old parts is going to be critical to being able to figure out how to make new things that replace them and keep those machines operating a little bit longer.
And that brings us to our can't miss articles. These are long form pieces written by our fantastic Hackaday writing staff. This week I wanted to pick Tom Nardi's Chip Shortage Engineering, Misusing Dip Packages. This is a really cool story. He started off wanting to make an SAO, a simple add-on for this year's SuperCon, because he's never done that before. And he did some prototyping with whatever he had on hand, which included a bunch of DIP 8 AT-Tiny 85s out of his closet. Then when it came time to get the PCB made, he discovered that the SSOP parts were fairly expensive, so he decided he would just make do with what he had in his closet. A tube of tiny 85s, but the dip ones. But the through-hole would kind of ruin the aesthetics of his add-on, so instead he decided to make his own custom footprints for kind of splaying the pins out on this thing and surface mount soldering the dip chip to it. And I thought that was really fun. What's neat about this article, if you've never done like footprint design in KiCad, is he kind of walks you through it. And this is, one of those oddball cases where you're absolutely going to have to make your own footprint. The other thing I thought was cool about this was he described this to me when we were talking about it, and I thought he was doing something that I used to do all the time back when I hated drilling holes in PCBs that I made at home, which is to fold the legs up under the chip. He's kind of like spreading them out and like gull winging them. I used to do the same thing, except to like physically fold the legs up and under, like actually some of those, whatever they are, there's those no contact ones. What are they called? Those old EEPROMs that you could plug them into the holders, the chip carriers?
Like a leaderless chip carrier, LCC?
Yeah, like a leaderless chip carrier. Their leads are kind of folded under. And the nice thing there is it works on the regular footprints too. Like you've already got pads in exactly the right place. But I like the way his looks, and I'll give that up. And finally, it's really cool because it's a trip back in time. And there was a time when these kind of flat pack they were called flat pack. These kind of flattened out dip chips actually predate dip chips with the leads bent down. They used to make these in finer pitch than the, 0.1 inch dips, but they were made for, very fancy at the time parts in the early 60s. The first time I saw these, it was actually in one of those Pace Learn to Solder videos, which are also marvelous. I'll have to find a link for those if you haven't seen the Pace Learn to Solder videos. It's from the 70s, and they're talking about how to solder these crazy chips, and I'd never seen them before. And that was my introduction to ceramic flat pat chips. Anyway, Tom has essentially reinvented those here. And the funny thing is they actually were easier to make because they were just putting the chips on these flat wire frames. And it wasn't until shortly afterwards that they decided, oh, we could fold the legs down and then stick them through holes. So Tom is now undoing all that progress that was made in the mid 60s and flattening his dip chips back out again, just because he's too lazy to go buy the right parts.
I don't think it was he was too lazy. I think it was that they weren't available,
Fair
right?
enough.
So I'm going to take up for Tom. That was actually my takeaway from this, is that just like I said, when you don't have a CRT, how do you make an oscilloscope, right? Well, when you can't find the parts you need, and I've been on that side of it a couple of times in the last couple of years where you go, oh, I need these parts. They're always available. Oh, wait, they're not
Right.
anymore, and no matter where, I mean, I've paid ridiculous prices for a couple of things where I've been able to find, 10 of them somewhere, and and sometimes you just can't even find the 10, and then you just pay out the nose to do something weird like this. So I thought that was really cool. I also thought about the flat packs, which, those were actually predate even ICs, because most of what you used to see in flat packs were actually hybrid circuits.
Ah,
And so that's actually a mill standard. I'd have to look it up, but it is a mill standard 18 something something that defines the flat pack. And you used to see that a lot in military and aerospace gear back in, the 70s or something. So yeah, I think it's an interesting thing, and I always think it's funny, and I don't know enough about the mechanical aspects of it, but when I was learning to solder, not with the Pace solder videos, when I was learning to solder, everybody said, oh, you got to make sure there's a good mechanical connection.
Yeah.
It's got to be in the, and now you just go slap some solder on it and it's stuck there. And I think it's because the surface mount components are small, right? I think it's that they don't have a lot of mass. And of course, when you've got a resistor a 10-watt resistor that's as big as your fist, well, it probably needs some mechanical support. I don't know that. I don't know what's changed to where, if you'd showed somebody this in the 70s and said, I just don't want to drill holes, I'm going to solder right to the pads, everybody would have turned their nose up at it. Now, whether that was because it really is a bad idea, or whether it's just because that's not how we do things, and therefore there must be some reason. That's how we've always done things around here, if you know that story.
like you say, it turns out to work as long as the pieces are small enough and nobody's trying to pry them off with a screwdriver. Or pull them off by extracting the USB connector off of the board, because there are times when only through-hole will do.
My pick this week was Jenny List's Retro-Tectacular: How Communism Made Televisions. I don't know what I liked about this exactly. It was just loved looking back at this old production line. And like, if you look at the title graphic from the thing, there's all these workstations with these little bitty CRT oscilloscopes that are probably, would be less than the $20 oscilloscope used to fix the Commodore 64 in the last segment, and probably cost, $5,000 a piece in those days. But I think what struck me watching the video was no wonder electronic stuff has gone down in price, right? And it's exactly for the things we've talked about. It kind of fits in. I didn't plan it this way, but it kind of fits in with the stuff we've been talking about. When you had to have some lady sticking components into a chassis and wrapping the wires around the posts and somebody was soldering them, and then that's expensive and would be even more expensive today, because in the 70s you didn't have to pay people as much. And so if you look at what goes into building these things in those days, and then go look anywhere and find a modern production line where a pick and place machine throws parts on a board, then it goes through a wave solderer, and a robot picks up the board and rinses it, and it's just a completely different operation. I think that was what really I found interesting. I guess too, and I've noticed this some in my own writing, being that I grew up during the Cold War and I grew up listening to shortwave radio, I think a lot of what went on, quote, behind the Iron Curtain, unquote, had a bit of mystique to it, right? So anytime we see the videos where they've tearing down some piece of Soviet era equipment or some of the Chernobyl stuff that they do, things like this, I think it's just interesting because I think you always wanted to see what was going on there. And for a variety of political reasons, they didn't want to tell us and we didn't want to have it, our side didn't want to disseminate it. So you didn't hear about any of this stuff. And so I think it's really cool that these days you can, in fact, learn a lot more about what was going on in their space programs, their manufacturing, their computers, their electronics. And it's actually, when you look at it, not that different from ours in a lot of ways and different in other ways. But I think that's actually an interesting counterpoint to the way we were brought up 20 or 30 years ago to think that that's different and it's completely not like us. Well, not really, which you always suspected.
Yeah, I don't know how much of this video to believe. This is, it's propaganda basically coming out of communist East Germany at the time. And like some of it probably is true and some of it probably is super rose-colored glasses. And it's really interesting to see in Germany here, there is kind of this wave of nostalgia, this nostalgia for the East German past, right? Back when the women who were working in the TV assembly factory would have, there's a picture here of the spa that they have or the gymnast, they have like an aerobics class and stuff. And whether this actually happened for everyone or I don't really know, but it's pretty funny. They have like night school for them. They have daycare. They talk about how many different daycares they have in this TV plant, right? Like it's all part of that old, communist shtick, right? And
it's the workers' paradise, Elliot. I mean, I believe that may have been somewhat true. I mean, they certainly had more equality in those days than the West did. Now maybe not in ways that you would like, right? That's another question. I don't want to be an apologist for that era, but I think a lot of our preconceptions about that is more from our education and it's propaganda on our side, right? Than it is a reality. And truth is, I think people everywhere are people, and we all kind of want to do well for ourselves and our families, and that gets reflected, right?
Oh, well, that's for sure.
So, I think the rest of it is all at another level. It was interesting when I used to listen to shortwave as a kid, though. You could always tell the tensions between the East and the West because you'd listen to Radio Moscow or Beijing or even Cuba. And, whether the news was like only mildly derogatory towards the U.S. or whether it was like, we have a report from our American correspondent and he'd come on and go, oh, yeah, every night there's looting on the streets and you can't go out and there's, fires and all this. You're thinking, where is this guy? I don't know. None of this stuff's going on in my town. I don't know. So, there was plenty of that going on both sides, I think.
I don't know. Propaganda aside, it is absolutely fantastic to watch the guys delivering the TV to the woman's house. Like she orders a TV, the two guys come out from the factory, they unload it out of the back of their car, they bring it upstairs, they adjust it just right, they plug it in. She's very satisfied. They pat the TV and they walk out the door. Like, you talk about the way things are cheaper now and why things are cheaper now. That's like, two people were driving out there for probably an hour and like adjusting her rabbit ears for her. Like that's got to cost somewhere, right? It's kind of a fascinating look at, this early 1970s assembly and how the factory worked and stuff too. So some of that's really cool as a time capsule, geopolitics aside.
Well, and just so we can take credit for having such a beautifully integrated program today, I would like to point out those TVs almost certainly were live chassis TV sets without transformers. I think Jenny even mentions that somewhere. So we clearly just had this totally organized and integrated. Yes. That's my story, and I'm sticking to it.
That wraps it up for this week's Hackaday podcast. Thanks very much for listening. To follow the links, head on over to hackaday.com/podcast. And if you see anything cool or do anything cool, shoot us an email, tips@hackaday.com. And until next week,
keep those hacks coming.
Why did I even? Damn it. I was going to say, are you having an emergency? Trick or... Bah. think we're set. I think I'm going to end on that.
It's probably one of those things that would make a good rant, but I don't know if it's podcasty.
I think we got to end on that.
What could possibly come after that? Yes. Well, I thought that would stop my recording.
I guess it's not digital signal processing.
It is digital signal processing if you're counting on your fingers, Elliot.